Hello, this is the luckiest maths teacher in the world, and today we're looking at the difference between irrational and rational numbers, which is an introduction to what we're going to do on surds. So when we say irrational or rational, we're not talking about those words in the normal everyday context, like most students being so irrational not wanting to do their homework. As with most things in maths, the definitions are black and white, they're very technical and very specific. So we're going to go through what they are. So I'm about to write up the definition of each, so please copy down if you like. Okay, so these are the definitions, so go through them carefully. So an irrational number is one that you can't write as a simplified fraction. So what we mean by that is a over b, where a and b are integers, whole numbers with no common factors, okay? So that's important. It's got to be a simplified fraction, because simplified means integers, because we can write anything as a fraction. I mean, we can write pi as pi over 1 or 2 pi over 2. But we need the top number, numerator, and the denominator to both be integers or whole numbers. So the second part is equivalent to the first. Now it's saying something slightly different, but what I mean by equivalent is they both imply the other. So if a number can't be written as a fraction, so if it satisfies this first condition, then this will also be true. If it can't be written as a fraction, then it can't be written as a terminating or recurring decimal. Similarly, if it can't be written as a terminating or recurring decimal, then it can't be written as a fraction, okay? Rational is just the opposite of irrational. All numbers are either irrational or rational. So rational numbers involve the vast majority of numbers that you've come across, numbers that you can write as a fraction or as a terminating or recurring decimal. So I'll go through some examples to hopefully elucidate this a bit. So let's look at some rational numbers first. So a number that you would have seen before, of course, might be like the number 4. Right? So 4 is the same as 4 over 1. So it's rational because I can write it as a fraction, as a simplified fraction, where 4 and 1 have no common factors other than 1. They have no proper common factors. So 4 is a rational number. Now something like 1/5, for example. Now we know it's rational because it's a fraction, but 1/5 is exactly the same as the number 0.2. They are at the same point on the number line. So I can write 1/5 as a terminating decimal. This is a terminating decimal because the numbers after the decimal place eventually stop. Therefore, it is a rational number. So recurring decimals mean that the numbers after the decimal point go on forever, but there's a pattern to them. So, for example, the numbers 0.11111 and so on, the 1 goes on forever. So that is rational because it's a recurring decimal, but if it can be written as a recurring decimal, then it can be written as a fraction. So this is actually just 1 over 9, okay? 1 over 7, for example, we know that's rational. That is 0.142857. So there's a lot of numbers after the decimal point, and it doesn't stop, but it repeats the pattern. It's 0.142857, 142857. So I can write this as a recurring decimal. So that's why they're all rational. Now what about some irrational numbers? Well, let's look at probably the most famous of them, which is pi. So you know that pi is the ratio of the circumference to the diameter of any circle. So pi is 3.14159265535 and so on, okay? So I haven't rounded, I've truncated it there. So after this 5 at the end, the numbers keep going on forever, but there's no pattern to them. You can't tell me, say, what will be in the 1,000th decimal place or the 2,000th. You can for 1 over 7. So we see here that there are 6 numbers after the decimal place. So I know that there'll be a 7 in the 6th, 12th, 18th, 24th decimal spots, but I don't know that for pi. I can't tell what will be in the 6th, 12th, 18th, 24th decimal spots. There is no pattern to them. So that's why pi is irrational. You can't write it as a fraction with an integer on the top and an integer on the bottom where they have no common factors. Another example of an irrational number is root 2, square root of 2. So we've come across these surds when we were doing Pythagoras. Now the square root of 2 can't be written as a fraction with integers either. Again, I could write it as root 2 over 1, but root 2 is not an integer. So because I can't write it as a fraction with integers, it is an irrational number. Now the square root of 2 is, if you put it on your calculator, 1.41421356, and then it keeps going. Again, there is no pattern to these numbers after the decimal point, and it goes on forever and ever. That is why square root of 2 is irrational, okay? So how's that going to help us with surds? Well, I'm going to explain that, but if you want to copy this stuff down, please do so now, because I'm about to go to a new slide. So surds are numbers involving square root signs. It turns out that the square root of anything that's not a perfect square is irrational. So, as I just said, so staying a bit more formally, square root of a is rational if a is a perfect square, but irrational if a is not. So the square root of, say, 49, that, as we know, is just 7. So that is rational because 49 is a perfect square. The square root of, say, 21, without even knowing what it is, I can tell you it's irrational because 21 is not a perfect square. So if you put that on your calculator, you'll see that it's 4.5825 and keeps going. So it fits our definition of irrational. It can't be written as a terminating decimal or a non-terminating decimal. So similarly for fractions, so the square root of a fraction will be rational if both the numerator and denominator are perfect squares. So the square root of a quarter is rational because 1's a perfect square, 4's a perfect square, this just equals a half. But the square root of, say, 3 over 4, that is not rational. It is irrational because even though 4's a perfect square, 3 is not. All right? Fantastic. So I just want to explain one more property of real numbers and then we're done. So again, copy this slide down if you want. So both the set of all rational numbers and the set of irrational numbers, they're dense subsets of the real numbers, which are all the numbers you know. So you're probably thinking, what is he talking about? So what this means in practice is that between any two rational numbers there is another irrational number, and between any two irrational numbers there is a rational number. Okay? So for example, let's say I have the number square root of 2 and I have the square root of 3. What I'm saying is that there will be both an irrational number and a rational number between these. Now finding a rational number isn't too hard because the square root of 2 is about 1.4142 and the square root of 3 is about 1.73. So to find an irrational number, I just need to find a number that has a terminating decimal, or I can use a recurring one too, but 1.5 is in between them. So that's a rational number between them. But there will also be an irrational number between them. So what I have to do that, all I have to do to find that is find a number between 2 and 3 and square root it. And that number itself can't be a perfect square. So I know, for example, that 2.5 is between is between 2 and 3. So the square root of 2.5, or the square root of 5 over 2, will be between 2 and 3. That's irrational because this number here, 5, is not a perfect square, nor is 2. Okay? So let's say I have two rational numbers. Let's say I have 10 and 11. So finding a rational number between them is easy. 10.5, you're done. What about an irrational number? Well, to find an irrational number between these two, I'm going to use the trick that I told you before. The square root of any number that is not a perfect square is irrational. So 10 is the square root of 100, because 10 squared is 100. 11 is the square root of 121. So to find an irrational number between these two, I can pick the square root of any number between 100 and 121. There are no perfect squares between 100 and 121 because 100 is 10 squared, and 121 is 11 squared. And if we square root a number that's not a whole number, if we square a number that is not a whole number, the answer we get is not a whole number. So hopefully that didn't confuse you too much. Essentially what I'm saying is 101, 102, 103, all the way up to 120, they are not perfect squares. So that means the square root of 120 will be an irrational number between 10 and 11. Square root of 102 will be an irrational number between 10 and 11. Square root of 101 will be an irrational number between 10 and 11, and so on. Hope you've enjoyed the video. This has been the luckiest maths teacher in the world. Have a great day.